Section 5.5, the substitution rule for integrals. To see this rule, we're going to first recall differentials from Chapter 3. For example, if we had y equal to 1 plus x squared, then we found the differential dy by the following. dy is equal to the derivative of y with respect to x dx, or y prime dx. So, using this, dy, if y is equal to 1 plus x squared, is just equal to the derivative with respect to x of 1 plus x squared, which is 2x, and then times the differential dx. So now let's see how that particular differential helps with the following integral. Here we have the indefinite integral of the integrand 2x times the square root of 1 plus x squared dx. If we replace 1 plus x squared with u, and then 2x dx with du, meaning I'm substituting u for 1 plus x squared, and then using differentials, the differential du will replace the 2x that's in the integrand and the differential dx. So replacing all of that, I will end up with this indefinite integral, the square root of u du. Notice that all I've done is take the square root of 1 plus x squared. That's the same thing as the square root of u. And the 2x and the dx, those are all just replaced with du. Then, integrating, square root of u is just the same thing as u to the 1/2 power. So then the antiderivative would mean increasing the power by 1. So u to the 1/2 becomes u to the 3/2. But then I have to divide by the new power, which means the same thing as multiplying by the reciprocal of 3/2. So then I have 2/3 times u to the 3/2, and then plus our constant of integration, capital C. And then resubstituting what we said u was, we get a final answer of 2/3 times the quantity 1 plus x squared raised to the 3/2 power plus capital C. So that is the integral of what we had started with. To check that this is true, you can just differentiate the answer that I've boxed up using the chain rule. So you can see that this idea of the substitution rule for integrals goes hand in hand with the chain rule of differentiation. So now we have a way to undo a chain rule derivative. So to generalize this, we get what is called the substitution rule. The substitution rule says if u is equal to g of x is a differentiable function whose range is some interval I, and if f is continuous on that interval I, then the indefinite integral of f of g of x times g prime of x dx is equal to the integral of f of u du. And again, you can notice here the notation in the integrand on the left. That should remind you of the chain rule, where you have a function evaluated at another function, and then this is being multiplied by the derivative of the function that's on the inside. So this is it. This is the whole section. But there is some difficulty with this, and that is, what do you use for the substitution? Sometimes for the substitution, you can start with the function that is inside another function, but sometimes that isn't as easy as it sounds, and so really it's just a little bit of trial and error, and then also practicing as many problems as you can. So let's start our practice with this first example. Evaluate the indefinite integral of sine of the square root of x divided by the square root of x dx. So we are integrating with respect to x, and we have this complicated integrand. And again, if you go back to the list of antiderivatives and indefinite integrals that we saw in section 5.4, you'd see that there wouldn't be anything on that list that would help you with this particular integrand. But we should notice that we do have a composite function in the numerator, sine of the square root of x. So we've got the square root of x as a function inside of the sine function. So, as a way to start, let's just take a guess for our substitution. Let's say u is equal to the square root of x. And that's really what you need to do when you're trying out these problems. Just start somewhere. If it doesn't work, it's okay. You just go start with something else. So if we start with u equal the square root of x, we should also remember that this is the same thing as x to the 1/2 power. So then the differential du just means that I'm going to take the derivative of x to the 1/2 with respect to x, which becomes 1/2 x to the negative 1/2, and then times the differential dx. So there we are using the differential definition that we saw all the way back in chapter 3. So now what you want to try to see is in your differential for du, something that looks similar to what you have in the original integrand. So as we look at it now, it's not quite the same, but maybe if we do a little rearranging, we would notice that 1/2 times x to the negative 1/2 is the same thing as 1 divided by 2 to the x to the 1/2 power. But while we're at it, how about instead of writing x to the 1/2 power, we write the square root of x. And now, what we see is a little bit of a pattern that looks similar to what we saw in the integrand. There's a square root of x in the denominator. That's good. There's a dx, the differential. That's also good. The only thing that's different is we have this 2 in the denominator. But constants can be dealt with very easily. If I have, at the end of this, du is equal to 1 divided by 2 times the square root of x dx, I can move that constant of 2 by multiplication. And you can always use this with the substitution method. You can multiply and divide by constants as much as you want. You can't add or subtract constants necessarily in this du or differential step, but multiplying and dividing you're pretty safe with. And if you notice, if I multiply both sides of the equation that I have here by 2, I would have 2 du is equal to 1 over the square root of x dx, which means I can replace the square root of x in the denominator and the dx that's part of the original integral with just 2 du. So putting this all together, the integral of sine of the square root of x divided by the square root of x dx is now exactly the same thing as, instead of sine of the square root of x, I have the sine of u. And instead of the square root of x in the denominator with the dx differential, this just becomes times 2 du. I've got a constant inside of my integrand. I can factor that out. So I just have 2 times the integral of sine of u du. And now I use antiderivatives. The antiderivative of a positive sine of u is a negative cosine of u. And then I need my constant of integration. And then finally at the end, I just need to plug back in what we said u was. So this becomes 2 cosine of the square root of x plus c. And again, if you were to differentiate what we just boxed up as our answer here with respect to x, you'll see that we go back to where we began. So let's just do that. Let's check. The derivative with respect to x of negative 2 cosine of the square root of x plus c. We know what's going to happen to the c. The derivative of a constant with respect to x is just 0. So using our chain rule notation, we would have a negative 2 times a negative sine of the function that was on the inside, and then times the derivative with respect to x of that function that was on the inside. Negative 2 times negative sine just gives me a positive sine of the square root of x. We've already seen that the derivative of the square root of x is just 1 over 2 square root of x. I needed to make sure I wrote down my 2 again, because now we see here that the 2's, the one that came about from what we started with and the one that came from this derivative, they cancel out, and that's what takes us back to sine of the square root of x divided by the square root of x. Something else that helps you practice and get better at integration is having a good handle on all of the functions that we've seen and learned about and their derivatives and antiderivatives. because you don't want to keep looking through lists when you're trying to think of things that you could use for substitutions. So in this example, this I actually took from the homework, we want to find the indefinite integral of 5 cosine of 6x divided by sine squared of 6x dx. So now here you may say, well, there's a 6x inside of a function. So what if I replace 6x with u? Okay, you could do that. Then taking the derivative, du would be 6 dx. And right here I'm just going to point something out that you want to maybe use as a guide. Doing a substitution for a linear function rarely helps you. And the reason why it rarely helps you is the derivative will always be a constant. And really all that you are doing is just switching out one differential for a constant times another differential. It actually doesn't change how difficult the problem was. So this is really not a good substitution. Okay, so now if that's not a good substitution, what else do we have to work with? Well, we've got sine and cosine here. There's a big alarm going off that is saying the derivative of one of those functions is related to the other function. So this is where knowing that the derivative of the sine function is the cosine function, or the derivative of the cosine function is a negative times the sine function. So now which one would you want to use? In general, it's a good idea to start with the functions that are in denominators, because when you take their derivative, you get other functions that, by the chain rule, would end up being in the numerator place. So it's a good idea to use, in this case, the sine function that we have in the denominator. And I'm not going to use sine squared 6x. I'm going to use sine 6x. Why? Because we need to remember that sine squared 6x means the same thing as sine 6x quantity squared. So this is a composite function. Notice we didn't use the 6x that's inside of the sine. We used the sine 6x that is inside of the squaring function. So we are still using the ideas of composite functions, but we're also using some facts about this whole function is in the denominator of this big fraction. So now let's take our derivatives. So du, the differential, is equal to the derivative of sine 6x, which would be cosine 6x, and then times, by the chain rule, the derivative of 6x, which is 6. But I'm going to write that 6 out front, and then I need my differential dx. So now notice we have what's in the numerator, cosine of 6x. And it doesn't matter that the 5 is not there. Remember, constants can always be dealt with by factoring out or multiplying and dividing if I need to work around with those constants. What I'm really focused on is I need to get the function. So I've got the function cosine 6x, and I have the differential dx, which means where I see it in the numerator and the differential dx there, I can replace that with, just by dividing by 6, 1/6 du. So I can replace the sine 6x with u, and I can replace the cosine 6x dx with 1/6 du. So then starting at the beginning, I have 5 cosine 6x divided by sine squared 6x dx. The 5 is just going to carry on through, and how about, while I'm at it, I'll just factor it out to the front of the integral. So there's the 5, and then I have my integral. Now I know that cosine 6x dx is going to be replaced by 1/6 du, and then the sine squared 6x, that's just the same thing as sine 6x quantity squared, which becomes the same thing as u quantity squared. You also want to be really comfortable with fractions at this point, because you're going to see a lot of them. The 1/6 that is in the numerator of this fraction that's in the integral, remember that's just the same thing as just 1/6 times the fraction du over u squared. I can also just factor that 1/6 out. And I'd have 5 times 1/6, which is just 5/6. And then my integrand, you could see it written as du over u squared. Or you could see that written as 1 over u squared du. Be comfortable with the fact that those are both exactly the same thing. Du over u squared is exactly the same thing as 1 over u squared times du. And then when you're trying to think of antiderivatives, now we've got a very simple function as our integrand. Here, I would recommend writing 1 over u squared as u raised to the power -2, because then you can see that you're just going to use the power rule for antiderivatives. So this means that I would have u to the -1, but then I have to divide by that new power. And the 5/6 is just going to multiply by that function, my constant of integration. I'm just going to use capital C again. So then all I have is -5/6 times u to the -1. Plus my constant of integration. And then now let's also plug back in what we said u was. So this becomes -5 over 6 sine of 6x raised to the -1. And we want to be very careful here. This is not the inverse function. This is just meaning the same thing as 1 over sine of 6x. So it would probably be cleanest to write -5 over 6 sine of 6x plus c. Okay, let's keep practicing with a few more. Find the indefinite integral of x to the 5th times the square root of 1 plus x squared dx. So now we've learned the substitution rule. This becomes one of many integration methods that you're going to learn as you're now transitioning from Calculus 1 to Calculus 2. And really the goal with this is practice, 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 because once you learn something, you then want to also learn that it can be manipulated in many different ways. So on this integral, I'm giving you a hint. If we let u equal 1 plus x squared, that's similar to what we did at the beginning of this lesson, but now we can also play around with the fact that this also means we can let x squared be u minus 1. Let's see why that becomes important. If I let u equal to 1 plus x squared, then as we saw at the beginning of the lesson, du is the same thing as 2x dx, which means I can replace x dx with 1/2 du, which is good because I've got a dx and I do have an x. It's there part of x to the 5th because x to the 5th is the same thing as x times x to the 4th. Now the only problem is that I don't have anything to replace x to the 4th with. You might ask, well, couldn't I just say that this is the same thing as x to the 4th, and maybe I could manipulate this thing and I could say that x is equal to 1/2 du dx, and I could raise that to the 4th, and then that would become, well, let's see, 1/2 to the 4th is 1/16, and then I'd have du to the 4th and dx to the 4th. And right there I would just ask you, okay, cool, what's du to the 4th equal to? Or what's dx to the 4th equal to? And you don't have an answer to that because you've never seen that notation before, ever. Raising a differential to a power does not make sense. So, all of that we cannot do. All right? So now, what do you do? This is why I brought up this hint. X squared is the same thing as u minus 1. Well, if x squared is the same thing as u minus 1, then what is x to the 4th? Well, that would just be the square of x squared, which is just the same thing as u minus 1 squared. So now you can see what we're going to do. I'm going to replace the 1 plus x squared inside of the square root with a u. And I'm going to replace one of the factors of x that are out front and the dx with 1/2 du. And then the x to the fourth I'm going to replace with u minus 1 squared. So now let me put that all together in one line to see all of those substitutions in place. Again, starting with what we have at the very beginning, x to the fifth times the square root of 1 plus x squared dx. I'm going to go ahead and split up that x to the fifth so that it's x times x to the fourth and then times 1 plus x squared dx. Okay, so now my substitutions. First of all, the 1 plus x squared. That's going to be replaced by u. Then I have the x and the dx. That's going to be replaced by 1/2 du. Then I also have x to the fourth. That's going to be replaced by u minus 1 quantity squared. So x dx, we said, gets replaced by 1/2 du. I split it up that way because this is all multiplication, and I have constants out front and differentials at the end. X to the fourth is replaced by u minus 1 quantity squared. And then the square root of 1 plus x squared is replaced by the square root of u. So now this doesn't look much easier, but you're about to see why it is. I'm going to factor that 1/2 out to the front. And then the u minus 1 squared, I'm going to actually multiply that out. So that's u squared minus 2u plus 1. And then instead of square root of u, I'm going to write u to the 1/2. And now distribute the u to the 1/2. Notice what you're about to get is just a whole bunch of power functions. So I have 1/2 times the integral of u to the 2 plus 1/2, which is 5/2, minus 2u to the 1 plus 1/2, which is 3/2, plus u to the 1/2. This is actually something that we can finish because this is all just power rule antiderivatives. So I have 1/2, and then times, this will be u to the 7/2, but then divided by the new power or multiplied by the reciprocal of 7/2, so 2/7, minus 2 times u to the 5/2, but then times the reciprocal of 5/2, so 2/5, and then plus 2/3 u to the 3/2, and then plus c. Again, you don't have to multiply c by the constant. If you did multiply capital C by 1/2, all you get is another constant, which again you could just write as c. So then multiplying through by 1/2, and then replacing all of my u's, 1/2 times 2/7 is 1/7. U, we said, is the same thing as 1 plus x squared. So I get 1/7 times the quantity 1 plus x squared to the 7/2, minus the 1/2 times the 2. They cancel, so I'm left with 2/5. And then u to the 5/2 is 1 plus x squared to the 5/2. And then 1/2 times 2/3 leaves me with 1/3. U to the 3/2, so 1 plus x squared to the 3/2. And then finally plus c. So that is our result. Looks drastically different than what we started with. But again, it's because of all of these manipulations that we just did. But you could certainly check this by taking the derivatives and then combining like terms at the end is really the way that you're going to see how that takes you back to the original integrand. Now that we've seen a bunch of examples with indefinite integrals, let's look at definite integrals. And with definite integrals and the substitution rule, you do have two options of what you can do with the limits of integration. You can evaluate the indefinite integral, like I've done with the previous examples, essentially setting aside the limits evaluating the indefinite integral all the way to the end, and then removing the constant of integration and plugging in your limits there. Or you can change the limits of integration along with the substitution. I prefer to use this second method, changing the limits along with my substitution, because that way I won't forget to do it at the end. So let me show you how that's used in this next example, which I also took from the homework. Use substitution to evaluate the definite integral given below. So here we have the integral from 0 to the square root of pi over 16. And the integrand is negative 2x sine cubed of 4x squared cosine of 4x squared dx. The integrand is pretty similar to one that we saw earlier, but now we have these limits of integration. So just like we saw earlier, I see a sine function and a cosine function. I'm going to pick the one that is being raised to a power. So it makes the most sense to use u is sine of 4x squared, because then the derivative of that will involve cosine of 4x squared also. And when I use the chain rule on this function to find its differential, I will get cosine of 4x squared, and then times the derivative of 4x squared, which is 8x, and then dx. So now let's just notice the things that we have. I've got sine of 4x squared, and it's part of this. It's just being raised to the third power. But then I also have cosine 4x dx, cosine 4x squared dx, which is there. And I also do have this x, which is up front. The only thing that's slightly different is I've got an 8 with my differential, and I have a negative 2 with the original integrand. But again, that's okay. What would you do to turn an 8 into a negative 2? You would just divide by negative 4, which means I could then write negative 1/4 du is the same thing as negative 2 x cosine 4x squared dx, which now I know exactly what to replace all of that with. Okay, so the original integrand is just going to become, I haven't replaced my limits yet, but I can at least replace the integrand. Negative 2x cosine 4x squared dx is going to be replaced by the negative 1/4 du. Again, I'm keeping my constant up at the front and my differential du at the end. Sine cubed of 4x squared, that's just u to the third power. Again, we know that this is going to be very simple to evaluate, but now let's just swap out our limits. And to do that, you want to just think that you have particular x values, like the lower limit of integration, the bottom one, is x equals 0. What happens when you plug x equals 0 into sine of 4x squared? You get sine of 0, and sine of 0 is u equals 0. So whenever x is equal to 0, sine of 0 is equal to 0, which means u is equal to 0. And then what about u equal to the square root of pi over 16? Well, if I take pi over 16 in the square root and then square it and multiply it by 4, because that's what 4x squared means, I would get 4 times pi over 16, which is pi over 4. And then what is the sine of pi over 4? It's square root of 2 over 2, which means when I have x equal to the square root of pi over 16, that's the same thing as u equal to the sine of pi over 4, which is the square root of 2 over 2. So now my limits of integration, the bottom one becomes 0, and the top limit becomes the square root of 2 over 2. So now using my power rule for antiderivatives, I have negative 1/4 times u to the 4th, but then I have to divide by the new power. I don't need a constant of integration because this is a definite integral. And I'm going to be left with negative 1/16 times the square root of 2 over 2 raised to the 4th power minus 0, raised to the 4th power. Notice I multiplied negative 1/4 and the 4 that was in the denominator. That's why I have the negative 1/16. And then square root of 2 over 2 raised to the 4th power is just going to be 4 over 16. And then negative 1/16 times, that's a 1/4. That gives me negative 1 over 64. So I recommend that you do this when evaluating definite integrals using substitution. Change out your limits along the way. Just keep track of everything that you're substituting and your new limits, and it becomes much easier because then you don't have to remember to do that at the end, and you don't also have to deal with the constant of integration. One application of the substitution rule is to get a couple more properties for definite integrals, and this relates to symmetry in functions that are even or odd. So let's suppose that f is a continuous function on the interval from negative a to a, which means the negative of a constant to the positive value of the same constant. Number one, if f is an even function, which means f of negative x equals f of x, then the integral from negative a to a of f of x dx is just equal to 2 times the integral from 0 to a of f of x. The reason for this is if you have an even function, it means that on either side of the y-axis, you have the same shape. So it's symmetric about the y-axis. So essentially this is saying instead of integrating from negative a to a, you could just do half of it and then multiply it by 2. So that's why we get that first property. The second property, if f is odd, which means f of negative x is equal to negative f of x, then the integral from negative a to a of f of x dx is equal to 0. And the reason for that one is essentially you have the same area, but one is above the x-axis and the other one is below the x-axis. So one of them is positive and the other one is negative. When you add those two areas, they just cancel each other out. So a good one to maybe think of with this is the sine function, which is positive, let's say from 0 to pi over 2, or in this case 0 to a like I drew, but it would be negative if you go the opposite direction. So then the areas that you have, one of them is above the x-axis, but then the same shape is below the x-axis, which means a negative area. When you add those two things, they cancel out and you're left with 0. So this is useful for other integrals where we can't actually solve them with methods that we've learned, but it does require that you memorize these properties. So if you do have methods where you can solve an integral, maybe try not to be tempted by these because you might actually use them improperly. So there's room for error if you mistakenly assume that a function is odd or even. But let's see how it actually works with this last example. Evaluate the definite integral of x to the 4th sine x dx, and our limits of integration are from negative pi over 3 to positive pi over 3. So first of all, we have no way of solving this with substitution. You will, in fact, learn how to solve this in the first week of Calculus 2. But let's see if we can use these properties. So let's say that f of x is our integrand x to the 4th sine x. And for seeing if it's even or odd, we just need to plug in negative x. F of negative x is negative x to the 4th, and then sine of negative x. Negative x to the 4th is positive x to the 4th, but sine is an odd function. So when you replace x with negative x, it's the same thing as negating sine x. And you can, again, try this out with sine of 30 degrees and sine of negative 30 degrees. You'll see that the results are opposites. So this actually ends up being negative f of x. So because of that, since this is an odd function, this is 0. And that's it. There isn't any antiderivative step that I have to use. I can just use the fact that my integrand was odd. And since my limits of integration is a negative constant on the lower limit and the positive constant on the top and they're both the same numbers, then my integral is just equal to 0.